everyone. Thank you for joining me for this example. Together, what we're going to do with this example is look at how to compute, how to come up with the geometry of a concrete pad supporting some kind of a force coming down from a building above. Now, we're going to be given the qualities of the soil that are supporting this pad, but one thing that I want to point out firstly and foremostly is this. This is a very simplified method according to Part 9 of the Ontario Building Code. Okay? So it's a good enough method for us to get some kind of dimension. It is not the exhaustive, appropriate method from a structural engineering point of view, but it's good enough because if you understand this method, then figuring out how to do it in a more complicated fashion from a structural engineering perspective, say to satisfy the requirements of Part 4 of the Ontario Building Code, is relatively simple, okay? As long as we understand how this works. And that's the point of this. So what do we have here? We have some kind of a concrete pier, say, measuring 400 by 400. It's transferring to this pad a force of 72.3 kilonewtons. This is coming from whatever it's supporting above. Say, the appropriate tributary area from the building above. What we want to find out is the length, width, and thickness of this concrete pad, knowing that that concrete pad is sitting on some kind of soil. And the soil in this case, I picked one. I went to table 9.4.4.1 of the Ontario Building Code. Again, we're using Part 9 for this example, a simplified method. Loose sand or gravel. The bearing capacity of that soil from this table is 50 kPa, which is another way of saying that the bearing capacity of this soil is 50 kilonewtons per meter squared, because that's what this is. kPa as a unit, and in this case, soil bearing capacity as a concept, is simply the amount of pressure that that soil can support before it can't take anymore. So if you apply more than 50 kPa on loose sand and gravel is not good enough to support whatever you put on it. And this is a unit per surface area, which makes it a pressure type force. Okay? So let's look at this conceptually. What we're basically looking at is to somehow balance out between themselves this applied force, which is a single force over a single point of 72.3 kilonewtons, against a bearing support, a bearing pressure that the soil offers over a unit area. Okay? And this unit area is over a space of 1 meter by 1 meter, basically. So what we have to basically try to figure out is what area gets these two quantities to balance. Look at it this way as an analogy. Say if you like to eat toast in the morning and to spread something on it. Let's pretend peanut butter. When you take peanut butter out of the jar with your spoon or your knife, it's in a big glob. It's a single amount, a force, say. But when you spread it over toast, you spread that amount over that surface area, right? And the thickness of the peanut butter over the toast, assuming that it's a uniform thickness, depends on the size of the piece of bread you're using, right? Bigger bread, thinner peanut butter. Smaller bread, thicker peanut butter, because you're taking that amount and you're spreading it over an area. So what we have to try to figure out is, given that we know what the applied force is from the building above, given that we know how much the soil is able to resist pressure-wise, what area can we get between these two that gets those two values to balance, right? Because we don't want a force that's more than what the soil can support. Okay? So that's what we're going to do, and let me show you how. So the first thing that I want us to remember is this. The bearing area, I'm going to call it A for short, is the ratio, so the fraction between the applied force, what we had here, And can you guess what's at the denominator? If we had this up here, what's going to go down here? It's going to be the bearing capacity. So another way to think about this is as follows. The area is the fraction between, at the top in the numerator, we're always going to put the force coming down because it's at the top. At the denominator, because it's at the bottom, we're going to put the soil because the soil is always at the bottom supporting that force. Okay? So what we're going to do is now put the values and units in here correctly. The applied force is 72.3 kilonewtons. As such, and the bearing capacity of the soil is 50 kPa, which is the equivalent unit of 50 kilonewtons per meter squared. Now this works because we have kilonewtons and kilonewtons both at the top and bottom. So when you cancel these units out, actually the unit you're going to get out of this is going to be in square meters. So when you do this division, 72.3 divided by 50, we get an area of 1.446 meters squared. So that is the area that gets the applied force and the bearing capacity to balance, because that's what we want, okay? Which means that if we put anything that's bigger than this area, we're able to spread that load, that peanut butter, if you will, over enough soil so that the soil can support it. If we have a pad that's smaller than this area, then we're going to push through the soil because the soil can't support it. Okay? So I'm going to write this up here. Area equals 1.446 square meters. So that's great. That's the first quantity we're looking for to figure out the length, width, and thickness. Let me make up some space here. So now that we know the area, right, the area of our pad, if we assume that that pad is a square, say, we remember that the area of a square is length times width, or length square, right? Because a square, both the length and the width have the same dimension. So if we want to solve for the length is equal to the square root of the area, just like that. Make sense? So then, when I do the square root of 1.446 square meters, what I get, and bear with me, I'm putting this down on purpose, is 1.202497412 meters. Now, why did I do something this silly? It's to illustrate a point, okay? When you calculate something, your calculator will give you something that's very, very precise. But what you get as a number using math is very different from what you can use then in real life in civil engineering. If you give this as the dimension of one side of your pad footing to somebody to build on site, they'll be disappointed, right? They might be even unimpressed, because there's no way to build something to this precision when it comes to civil engineering construction, okay? For the kind of stuff that you and I work on or live in. And there's no need to get this precise. Heck, usually on site, when you build something within the 5 to 10 millimeters, that's good enough, usually, okay? So what we need to do is decide what kind of level of precision we're looking for. And that's where you would ask your supervisor, your boss, okay? Or it would be established in your company. For us, for the purposes of this example, let's assume we're going to go to the nearest, 5 millimeters, like that. Okay? And what you do then is you find where millimeters are. If this is meter, millimeters is right there. So then you rewrite that answer to the closest 5 millimeters, and you always go up right? You don't go down, you always go up. Why? I mean, going down is closer, right, than going up. Why do you always go up? Because if you go down and try recalculating your area using this dimension, you come up with an area that's less than that. And that's no good. What we found here, if you remember, is the minimum area so that this pad does not sink in the soil, right? So that the soil is strong enough. If you come up with down rounding, the area becomes smaller than the minimum you require for the balance to happen between the applied force and the resisting soil. So you always have to round up, okay? So let's call this 1.205 millimeters, okay? Now, you might even find that depending on the kind of construction that you're doing, if it's residential, sometimes you might even be asked to round to the nearest 10 millimeters, nearest 100 millimeters, okay? So if that's the case, round up appropriately. But in our case, let's assume this is good enough. The length equals the width equals to 1.205 meters squared. Now, if you wanted to check that this was okay, find the area using this dimension, and it should be equal to or greater than this area. Never less. Okay? That's a good way to check. Okay, so what we found now is that the length, the width are calculated. We have found these two. So I'm just going to put this in here. I'm going to call it 1.205 meters, like that, okay, for this width. The next thing we have to find is the thickness. What is the thickness? What is the thickness of this pad? Well, according to 9.15.3.8 of the building code, because we're using a simplified method, this thickness is the smallest of two dimensions. Either it's 100 millimeters, or it's a projection. So again, go look this up, 9.15.3.8. Okay, so this thickness is either 100 millimeters or this projection, whatever that is. What is this projection? This projection is actually this dimension I'm about to show you. It's this dimension right here, which I'm going to show in green. Okay? It's the projection beyond the edge of the pier we're supporting. Right? That's the projection there, which is the same projection here. It's this dimension. Another way to look at it, the projection is this dimension. How much the pad extends past the pier it's supporting. Okay, so once you find this projection, it's the same projection here, it's the same projection here, and it's the same projection there. So how do we find that? Well, actually for us, that's relatively simple. We know this is 400, right? The pier that's coming down on this is 400 by 400. We now also know, again, millimeters, we now know also that the width and length of the pad are 1.205 meters. If we convert that to millimeters, if we want to use consistent units, if we know that this is 1,205 millimeters, we know that this is 400, and these are going to be the same. Can we find what these are? For sure. We're going to do this number minus this number, and whatever is left, we divide by 2 to get one of them. So let me write that out for you. Projection is, in our case, 1,205 millimeters minus 400 millimeters. And then whatever this answer is, we divide by 2. Like that. So when we do that calculation, what do we get? I'll do it in real time with you. 1205 minus 400, and then divide that by 2. Okay. I get 402.5 millimeters. That's the thickness. Right? So again, the thickness is either this or this projection. Which one do we pick of the two? You always pick the bigger one. So in our case, we're going to pick the projection because the projection is bigger than that. Are we done? No. Remember this? If you give a thickness that is to a 0.5 millimeter, okay, there is no point in doing this on a job site where the ability to measure something is less or more than 0.5 millimeter. Okay? So what you do is you give it to the nearest 5 or 10 millimeters depending on what you're expected or what's clarified for you. In our case, let's say we're doing it to the nearest 5 millimeters. Right? So that's going to be for this value here, which is going to give us 405 millimeters. Always round up. So now we're done. We have this thickness of 405. We can summarize our final answer. I'll do it right here. Therefore, the dimensions of the pad, the concrete pad, are length times width times thickness. So the length, I'll do it in millimeters. 1205 by 1205 by, the thickness is 405 millimeters. And then I'm going to make this answer obvious and unmistakable. Like that. Okay? So what we did with this example is a simplified way of figuring out the dimensions of a concrete pad according to Part 9 of the Ontario Building Code. It's a simplified method. More complicated methods of doing this are available and is what's used by structural engineers, but they simply build upon this. As long as you understand that figuring out these dimensions is about figuring out an area that balances the applied force and the bearing resistance of the soil, balances the two, then you're good. Thank you so much for your time and take care.